everyone, and welcome back to Desktop Math. Today, we're going to be talking about exponential functions. So, what exactly is an exponential function? Well, it's a function whose value is a constant raised to the power of its argument. So what exactly does that mean? And how do you form a function? So, in order to form a function, we let the independent variable be the exponent. So let me show you what that looks like. So we have f of x equals 2x. Now when graphing this, we see the line that looks like that. And as that rises, we see that that's a growth. So exponential functions describe growth and decay. We notice that 2 is greater than 1, so this graph describes growth. Now what's an example of a decay graph? Here's one. We have g of x equals 1/2 raised to the power of x. And as we can see, this is a negative slope, so it's decaying. Also, as we can see here, 1/2 is less than 1, so it's decay. So, an example of an exponential function that we can use in our everyday lives is interest rate. So, the formula for interest rate is A equals P times 1 plus R and then to the T. So, let's put what we know in our formula to work. So, we have the problem. In order that a $10,000 investment grow to $20,000 in 7 years, what must be the annual rate of interest? And we're assuming that the interest is compounded as well. So, we use our handy-dandy formula that we have, and we plug in what we know. So we know that A equals 20,000, P equals 10,000, and T is 7 years. So now, we plug it into our formula, and this is where we're at. Then, with some really cool algebra, we get R equals 0.14, or 10.4%, which is the annual interest. Okay, pretty easy, right? So let's move on to something a little bit harder. So what we're going to be using is we're going to be using this equation. PT equals 5,280 times 1.024 to the T. Now this equation is going to describe a small town whose population has been growing at an annual rate of 2.4%. Now this question is going to have 3 parts. Part A, B, and C. Now, let's get started on part A. So part A, what is p to the 0 and what is its meaning? So when we plug in 0 into the function that we were given, so we have pt equals 5,280, this equation that we were given already, and what happens when we plug in 0 to t? Well, once we plug it into the equation and we do some super cool algebra, we get p to the 0 equals 5,280. That's the initial population. Whoa. So, now we're going to move on to part B. What is t when the solution equals 10,560? So that is what we're trying to find. So, once again, reviewing the formula that we have, we're going to go in and plug in what we know. So once again, after we've done some super cool algebra and we've plugged in what we know, we get that t equals 29.23. I can feel it. You're getting smarter already. Part C. Calculate p times negative 30. P to the function negative 30. What does this number mean? But we're going to find that out. So, once again, reviewing the formula, we're going to plug in what we know. So we're trying to solve for t, and this is the equation that we're given. And we plug in negative 30 into t, and we're trying to figure out what it's going to turn out to be. So, after some super cool algebra, and plugging in everything into what we know, we get that p negative 30 equals 2,592. So we figured out in part A that p of 0 is 5,280. So if p negative 30 is less than the initial, then that must mean that p negative 30 is 30 years before the initial. Now, these are just a few example problems and things that you guys have been learning. But exponential functions have a bunch of different things that you can be learning about. And they're very tricky and some are very interesting. And they range from interest rate problems to graphing decay and growth to much, much more. Now, I hope you guys all had a great time with desktop learning, and thank you for watching.